Welcome to the deep dive. You know how this works. We gather your source material, we sift through it, and we pull out the most interesting nuggets of knowledge. If you enjoy what you hear, hit that like button and subscribe to the Deep Dive canal so you don't miss an episode. Today we are diving into the fascinating world of physics, specifically the fundamentals of motion, speed, velocity, and acceleration. And to help us navigate this exciting world, we have a fantastic expert with us. I'm so excited to get started. I mean, we see things moving around us all the time, like cars and bikes, or even just a ball falling to the ground. But how would a physicist describe motion, like in a scientific way?
It's all about visualizing it. Imagine a car going down the road. As time goes by, its position changes. We can plot those changes on a graph with time on one axis and position on the other. That graph is like a map of the car's motion.
It's like a story of the car's movement.
Yeah.
That makes sense. Thinking back to my physics classes, I remember that classic example of a falling object, like a ball, tracing out a parabolic curve as it falls. Isn't there a formula to describe that path?
There is. For a simple falling object, the formula is S equals 16t squared. S is the distance the object falls, and t is the time it takes to fall.
Oh yeah, that formula rings a bell. What's the significance of that number 16?
That's a great question. It represents half of the acceleration due to gravity, which is about 32 feet per second squared. The formula captures how gravity pulls the object down over time.
That's super cool. It's like a hidden code for how gravity works. Okay, let's talk about speed. We use this word every day, but I'm guessing physicists have a more precise definition.
You're right. Even the concept of speed has been debated for ages. There's a famous thought experiment, Zeno's paradox. It's about a race between the super-fast Achilles and a tortoise.
A tortoise.
Yeah, the tortoise gets a head start, and Zeno argued that Achilles could never catch up.
Wait, how could Achilles lose? He's supposed to be incredibly fast.
That's the point of the paradox. Zeno said that to catch up, Achilles first has to reach where the tortoise started. But by then, the tortoise has moved forward a bit. Achilles has to cover that new distance, but again, the tortoise has moved on. It's an infinite loop of almost catching up.
That's so frustrating. How do we make sense of that? It feels like we need to go beyond just regular speed.
Exactly. Zeno's paradox forces us to think about speed over really tiny distances and time intervals. To define speed at any given instant, we need to make those intervals smaller and smaller. Infinitesimally small, in fact.
Infinitesimally small. Okay, I think we're getting into some serious math here.
We are. This is where calculus comes in, specifically the concept of derivatives.
Ooh, derivatives. My calculus is a bit rusty, to be honest.
Think of it like taking a snapshot of the object's position at two moments very, very close together. The derivative, written as ds dt, gives us the rate of change of distance, that's s with respect to time, at that exact instant. It's the instantaneous speed.
So we're zooming in on a tiny slice of time to see how fast it's moving right then and there.
Precisely. Remember our falling object formula, s equals 16 Tolli. To find the speed at, let's say, 5 seconds, we would use the derivative of that equation.
And how do we actually do that? I'm really curious to see how this works in practice.
It does involve a bit of math. The derivative of s 16 Tolli turns out to be 32t.
So to get the speed of 5 seconds, we plug in 5 for t.
That's it. We get 32 times 5, which equals 160 feet per second. We just calculated the precise speed of our falling object at a specific moment.
Wow, I never thought I'd see calculus in action like that. It's amazing. Now, let's say we don't have the distances, but instead have a table of speeds at different times. Can we figure out the total distance traveled?
Yeah, that's where we use another powerful tool from calculus, the integral.
I've heard of integrals, but I don't really get what they are. How do they help in this case?
Imagine taking those tiny speeds over tiny time intervals and adding up the distances traveled in each little piece. That's basically what an integral does. It's the reverse of taking the derivative.
So if derivatives tell us how fast something is changing, integrals tell us how much it has changed overall.
Exactly. We're putting together the information from those little snippets of speed to reveal the big picture, the total distance.
I'm starting to see how powerful calculus is. It's like we have these new tools to understand motion.
They're essential for understanding all sorts of things in physics. Let's move on to acceleration now.
Okay, acceleration. I know it's related to speed, but how is it different from velocity?
Well, acceleration is all about how velocity changes over time. It's not just about speeding up, but also about slowing down or even changing direction.
So like if a car slams on the brakes, that's acceleration too, even though it's slowing down.
You got it. Or imagine a car going around a bend at a constant speed. Even though the speed is steady, It's still accelerating because the direction is changing.
Ah, I see.
Mhm.
Acceleration is a broader concept than I first thought.
It is. And just like with velocity, we can talk about average acceleration over some time or instantaneous acceleration at a precise moment. Actually, instantaneous acceleration is also a derivative, dv/dt. That is, the rate of change of velocity over time.
So if we know a car goes from 0 to 60 mile per hour in, let's say, 6 seconds, we can calculate the average acceleration, but we can also use derivatives to find out the acceleration at any moment during those 6 seconds, right?
Exactly. It's like using a microscope to zoom in and see how the car's velocity changes from moment to moment.
This is so fascinating. We're building up this whole toolkit of concepts and math to really understand motion.
We are. And these tools become even more powerful when we start exploring how forces influence motion.
That's a great point. I'm curious about how forces fit into all of this. Motion, speed, velocity, acceleration.
Forces are like the drivers of these changes in motion. Newton's second law of motion describes this relationship. It says force equals mass times acceleration, or sigma.
So a bigger force leads to bigger acceleration.
Right. And that's why a heavier object needs a larger force to have the same acceleration as a lighter object. Imagine pushing a shopping cart. A full cart requires more force than an empty one to get it moving.
That makes sense.
Yeah.
But what is force exactly? I mean, I can feel it, but how do physicists define it?
Force is any interaction that can change the motion of an object. It's a push or a pull, and it's a vector, which means it has both magnitude and direction.
So when I push a box across the floor, I'm applying force with a certain amount of strength in a specific direction.
Exactly. And that force is what causes the box to accelerate in that direction.
Okay, I'm starting to see how these concepts all link together. Force leads to acceleration, which affects velocity, which ultimately describes how things move.
You've got it. And understanding this is fundamental to physics and to understanding how the universe works.
This is incredible. It feels like we're just scratching the surface of understanding motion. I can't wait to learn more about how this all plays out in the real world.
There's so much more to explore. We'll be back soon with part 2 of this deep dive, where we'll go even deeper into these fascinating concepts. Welcome back to the deep dive.
It's great to be back. I'm still thinking about all that stuff about motion, speed, velocity, acceleration, even a bit of calculus. It's amazing how it all fits together.
It really shows how elegant physics is,
Yeah.
how these basic ideas can explain so much about the world around us.
For sure. You mentioned how forces influence motion, and I remember learning about Newton's laws of motion. They always seem super important. Could we break those down a little more?
Absolutely. Newton's laws are a foundation of classical mechanics. They tell us how objects move and how they interact because of forces.
Right. And the first law, if I remember correctly, is all about inertia. An object at rest stays at rest, and an object in motion stays in motion at a constant velocity unless some force acts on it.
You got it. It sounds simple, but the idea of inertia was revolutionary. Before Newton, people thought objects would naturally slow down and stop on their own. Inertia shows us that objects actually resist changes in their motion.
So if I slide a hockey puck across a perfectly smooth ice rink with no friction, it would keep going forever, at least in theory.
Precisely. Of course, in real life, there's always some friction, air resistance, and other forces acting on things. But the principle of inertia helps us understand why objects tend to keep moving in a straight line at a steady speed unless something pushes or pulls them.
Makes sense. Now, Newton's second law, that's the one with the famous equation FMA, force equals mass times acceleration. Why is this law so important?
It gives us a way to measure the relationship between force, mass, and acceleration. It tells us how much an object's motion will change when a force is applied. More force means more acceleration, and a heavier object needs more force to get the same acceleration as a lighter one.
So like pushing a shopping cart.
Yeah.
A full one needs more force to get moving than an empty one, right?
Oh,
That's
yeah.
FMA in action.
Exactly. This law is super powerful. We can use it to predict how things will move when forces act on them, whether it's a ball thrown in the air or planets moving around the sun.
Wow, so Newton's second law applies to everyday objects and huge things like planets. That's awesome. What about his third law? That's the one about action and reaction, right?
You got it. For every action, there is an equal and opposite reaction. Whenever one object exerts a force on another, the second object pushes back with the same amount of force in the opposite direction.
So when I jump off a diving board, I push down on the board, and it pushes back up on me with the same force.
Exactly. That upward force from the board launches you into the air. You wouldn't be able to jump without it.
I like that picture, like an invisible spring pushing back.
Yeah.
We've talked about Newton's laws, but I'm curious how they work in more complicated situations. You mentioned planets going around the sun. How do those laws explain that kind of motion?
Great question. Newton's laws, together with his law of universal gravitation, perfectly explain how planets move. Everything with mass attracts everything else with mass. The sun, because it's so massive, exerts a huge gravitational force on all the planets.
So it's like the sun's gravity is an invisible string, keeping the planets in orbit.
That's a good way to think about it. The planet's speed and the shape of their orbits depend on the balance between their inertia wanting to move in a straight line and the sun's gravity pulling them inward.
Like a cosmic dance between gravity and inertia. What about when objects collide? How do Newton's laws help us understand what happens?
Collisions are a great example of these laws at work. Imagine a classic physics demo. Two billiard balls with the same mass colliding head-on. One ball is moving, the other is at rest.
Okay, I'm picturing it. So what happens when they hit?
The moving ball hits the stationary one and exerts a force on it. According to Newton's second law, that force makes the stationary ball start moving. It accelerates.
And the stationary ball pushes back on the moving ball, right? So the moving ball slows down. That's Newton's third law.
Exactly. In an ideal scenario where no energy is lost, the moving ball would completely stop, and the stationary ball would move away with the same speed the first ball had.
So they basically switch their motion.
Right. During this collision, another principle is at work: the conservation of momentum.
Momentum. We haven't really talked about that yet. What exactly is momentum?
Momentum is a way to measure how much oomph a moving object has. You calculate it by multiplying the object's mass by its velocity. A heavier object moving at the same speed as a lighter object will have more momentum.
So a bowling ball rolling down the lane has more momentum than a tennis ball rolling at the same speed.
Precisely. One of the most fundamental laws in physics is the law of conservation of momentum. This law states that in a closed system, the total momentum stays the same, even if the objects in that system interact with each other.
So in our billiard ball example, the total momentum before they hit, which is just from the moving ball, equals the total momentum after they hit, when the other ball starts moving.
That's right. Momentum is transferred from one ball to the other, but the total amount stays the same. This is a really helpful idea for understanding collisions, especially when the forces involved are complicated and hard to measure directly.
So even in something chaotic, like a multi-car crash, the total momentum of the system remains constant.
Correct. Of course, in real crashes, some momentum is lost due to things like friction and heat, but the principle of conservation of momentum still holds true for the most part.
That's really cool. It's like we're discovering these hidden rules that govern how the universe behaves. You said that momentum is conserved in a closed system. What exactly is a closed system?
A closed system is like a bubble where no matter how can get in or out, and there are no outside forces acting on it. It's totally isolated.
So our billiard ball example is a closed system because only the two balls are interacting and we're ignoring things like friction.
Exactly. But if we were to think about, say, a ball rolling on a carpet where there's a lot of friction, then that's not a closed system. The total momentum wouldn't be perfectly conserved.
Got it. So we need to be careful about defining what we're looking at to use these principles correctly.
That's an important point. Defining the system is essential when we're using these fundamental laws of physics. It lets us focus on the specific interactions and make accurate predictions about what will happen.
This is really exciting. We're building this whole framework for understanding how the universe works. Now, I know there's always more to learn, especially when it comes to physics. What other amazing things will we explore in the next part of our deep dive?
I'm glad you're enjoying it. In part 3, we'll delve into some real-world examples of these physics principles, like how rockets work, and we'll even touch upon how our understanding of motion has evolved since Einstein.
That sounds fantastic. Can't wait. Welcome back to the deep dive. It's amazing, all these physics principles we've been talking about. Forces, momentum, Newton's laws. It's like seeing the world in a whole new way.
It really is.
I know. It's mind-blowing how these simple laws can explain such complex things. In the last part, you mentioned looking at some real-world applications, like how rockets work. I was wondering about that. How do we launch these massive rockets into space?
Rocket propulsion is a perfect example of Newton's third law. For every action, there is an equal and opposite reaction. In a rocket, the action is the expulsion of hot gas out of the nozzle at super high speed.
So the rocket is basically pushing something out, and that pushes it forward.
Exactly. That's thrust, the force that propels the rocket in the opposite direction. Imagine you're on a skateboard and throw a heavy ball forward.
I definitely roll backwards.
Right. The ball exerts a force back on you, pushing you in the opposite direction. A rocket engine does the same thing, just on a much bigger scale. And the faster those gases are expelled, the greater the thrust and the faster the rocket accelerates.
It's all about the power of that push. But rockets also had to fight against Earth's gravity to reach space. How does that play into it?
That's where escape velocity comes in. It's the minimum speed something needs to escape the pull of gravity from a planet. For Earth, that's about 11.2 kilometers per second. Super fast.
Wow, that's incredibly fast. I bet it takes a ton of fuel to get up to that speed.
It does. Rockets carry a massive amount of fuel, which gets burned and expelled to create the thrust needed to reach escape velocity. The challenge is to make the rocket as light as possible while carrying enough fuel to break free of Earth's gravity.
It's amazing how engineers have figured that out. You know, earlier we were talking about something called the relativity principle. You said physics would look the same whether we're standing still or moving at a constant speed in a straight line. Could you explain that a bit more?
Sure, that's Galilean relativity. The laws of physics are the same for all observers who are moving at a uniform speed.
So if I'm doing a physics experiment on a train, moving at a steady speed on a straight track, the results would be the same as if I did it in a lab that's not moving.
Exactly. There's no special or preferred frame of reference. All motion is relative. It's an elegant concept.
It is. But it's kind of counterintuitive, too. We experience motion all the time.
Yeah.
And it feels very real.
True. But think about this. If you're on a train moving smoothly at a constant speed, and you drop a ball, what happens?
It falls straight down. Just like if the train were stopped. I've noticed that.
Right. It's like the ball doesn't know the train is moving. From your perspective on the train, there's no difference. Someone standing on the ground would see the ball move in a parabolic path, but you just see it fall straight down. Both observations are correct. It just depends on where you're observing from.
Wow. So the laws of physics hold true no matter how we're moving, as long as that motion is steady and in a straight line.
That's the essence of Galilean relativity. But you might be wondering if this always holds true.
Yeah, actually, I was just thinking about that. Are there times when this principle doesn't apply?
Well, in the early 1900s, physics was revolutionized by Einstein's theory of special relativity. When we start dealing with things moving at incredibly high speeds, like close to the speed of light, things get a bit more complicated.
This is where things get really mind-bending, right?
You could say that.
Yeah.
One of the key things about special relativity is that the mass of an object is not actually constant. As it gets closer and closer to the speed of light, its mass increases.
Wait, so the mass changes? That's crazy. I always thought mass was like a basic property that never changed.
It's a common misconception. But at those extreme speeds, we have to adjust our understanding of Newtonian physics. This increase in mass affects momentum. So at everyday speeds, the usual formula for momentum, PMV, works fine. But at these relativistic speeds, we need to modify it to account for the changing mass.
So the faster something moves, the heavier it gets, and that changes its momentum.
Precisely. And this has a profound implication. There's a speed limit in the universe. As an object approaches the speed of light, its mass approaches infinity, which means you'd need an infinite amount of energy to accelerate it further. That speed limit is, of course, the speed of light itself.
That's incredible. So even the most basic laws of physics need some adjustments when we're dealing with these extreme situations. But even with those changes, the idea that momentum is conserved still holds true in special relativity, right?
Exactly. It's just that we have to consider relativistic momentum, which takes into account the changing mass at those high speeds. This has been experimentally verified countless times, and it's one of the foundations of modern physics.
This deep dive into physics has been absolutely mind-blowing. From the basics of motion and speed to mind-bending ideas like relativity. It's amazing how these principles govern the universe at every level.
It really is fascinating.
It's been an incredible journey. And a huge thank you to our expert for guiding us through this amazing world of physics. And to all of our amazing listeners, thank you for joining us on this deep dive. We hope you've enjoyed exploring these fundamental concepts as much as we have. The world around us is full of fascinating mysteries, and physics gives us the tools to unlock them.
It certainly does.
Don't forget to like and subscribe to the Deep Dive canal so you don't miss our future deep dives into all sorts of interesting topics. We'll be back with another episode soon, so stay tuned. From all of us here at the Deep Dive, thank you for listening.